Let's switch topics a little bit and talk about bases. So strong bases are more willing to accept protons. We use water as the standard acid, just like we used it as the standard base when talking about acids. For ionic bases, so salts that have OH in them, typically all of the units are dissociated into OH minus, which means that they can accept H's. It's a strong electrolyte. And this part's important, multi-OH strong bases completely dissociate. So things like MgOH2, you're going to get 2 hydroxides for every unit of that you dissociate. So like it's showing here, the OH minus concentration is the strong base concentration times that number. So let's practice. Calculate the pH of the following strong acid or base solutions. So you can pause the video and practice this. So a 0.002 molar HCl, our pH is going to be the negative log of 0.0020, which is 2.70. For our calcium hydroxide, our pOH is going to be the negative log. There are 2 hydroxides for every unit. So we're going to have 2 times our 0.0015. So our pOH will be 2.52, which means my pH is 14 minus 2.52, which is 11.5 or 11.48. So there we go. What about weak bases? So weak bases only accept a small fraction of the H's. They're weak electrolytes, just like weak acids are weak electrolytes. So for example, ammonia in water is in equilibrium with the ammonium ion and hydroxide. So finding the pH of a weak base is going to be similar to finding the pH of a weak acid. We're just going to have one more step in there. Just like we used a Ka for weak acids, there's a Kb, the base ionization constant for weak bases. Base strength is measured by the size of the equilibrium constant. We use the Kb. The larger the Kb, the stronger the base. And the Kb is going to be your hydroxide concentration times the conjugate acid divided by the base concentration, which should make sense once we look at an example. Here are some common weak bases to keep an eye out for. Carbonate. So you're going to need some sort of positively charged ion to balance it out, but it's not going to affect the reaction. So carbonate's a big one. Amines, ammonia, the bicarbonate ion. So just things to keep an eye out for. Typically you'll be told that they're weak bases. Amines are, the structure of ammonia. They are, instead of having hydrogens on the nitrogen, one or more of them is replaced by a carbon, but you still have that lone pair of electrons that can accept an H+, fitting our definition of a weak base. So let's practice. Find the pH of 0.1 molar ammonia. We have our equation here with our weak base. Ammonia reacting with water gives us the ammonium ion and hydroxide. Our initial concentration of our ammonia is 0.1. We're going to lose some from our initial base. We're going to gain some acid and OH minus. We have our Kb for ammonia. And so our 1.76 times 10 to the minus 5 is equal to, and again, we can use our x as small approximation. So it's going to be x squared from those x's divided by 0.100. We can solve for our x. And our x value is 1.33 times 10 to the minus third, which, remember, in this case is our hydroxide concentration. So then we can find our pOH from that. If we take the negative log of that, we get a pOH of 2.88, which means our pH is 14 minus that, which is 11.12. 0.124, yeah. Okay, another practice, I would recommend pausing and working this through on your own. Find the pH of a 0.0015 molar morphine solution. Morphine is another amine. The Kb of morphine is 1.6 times 10 to the negative 6. So our generic base plus water is in equilibrium with our conjugate acid plus OH minus. We're going to have, we're starting with 0.0015 minus x plus x. So got my ice table, and again I can use the x is small approximation. So 1.6 times 10 to the negative 6th is x squared over 0.0015. So I can find my x. So my x is 4.8989. So 4.90 times 10 to the minus 5th. So my pOH is 4.31, which means my pH is 9.69. So that was just 14 minus 4.31.